Well, the next speaker is me. So what am I going to be talking about? Let's see. Well, let's find out in just a minute, okay? Got to take this. I know. So I'm David Pyne, and I'll be talking about the conjunctive use of aquifer storage recovery, wells, and desalination to mitigate saltwater intrusion and achieve water supply reliability. So this is there we go. So I think by now, after 2 days of this meeting, there's no question as to what is aquifer storage recovery, but just in case you just signed up today, we're talking about storing water in a well during times when we have extra water available of good quality, and then recovering it from the same well. And basically a very simple concept. So we started out thinking that ASR was just something you did to store water in wet months and recover during dry months, typically within 1 year. And that was the case for the first several projects, and then we started running into people who said, well, yeah, that's of interest, but we're really concerned about droughts. And then we ran into some folks who said, well, our main concern is emergencies, hurricanes, floods, pipeline breaks, those kind of things. Anyway, over the years, we've now wound up with 30 different applications of ASR. So I'm just going to talk about 3 of them today. But just be aware that the starting point on any MAR program that's using wells should be to take a look at this long list of 30, figure out which ones are of interest to you, and prioritize them. What's your most important one? What are the second, third, fourth, fifth? Usually there's 4 or 5 applications, and if you go through that process, you're going to wind up with a well or well field that's in the right location or locations and is in the right aquifer or aquifers. And if you skip that step, which happens all the time, usually we go to a place and they say, well, we've already figured out which well to use, that one right there, and it's in that zone, so just work with it. Well, that is the wrong way to start. So anyway, just be aware that there are many applications, and this is a key initial step for success with ASR. So this is, 8 or 10 of the 30, and these are the more common applications. So I already talked about the first 3, the seasonal storage, the water banking and long-term storage, emergency storage. But what about disinfection byproducts? If you have them in the water under certain conditions that occur at most ASR sites, but not all of them, you can get rid of disinfection byproducts. It happens naturally due to microbial activities underground. Raising water levels. We just heard from the previous speaker about the water levels declining. This is happening all over the world. So restoring water levels with ASR is a common application. A lot of places, they have a lot of water on one side of town, but at the other side of town, they have low pressures, and having an ASR well located on that side of town can enable you to maintain system pressures without having to put in a long transmission pipeline, and that's a very cost-effective application. And then there are places where you've got low flows at certain times of the year, like on the top of a hill in a tourist area or something like that. And it's a great place for an ASR well to maintain flows and thereby avoid distribution system water quality problems. Some utilities use ASR primarily for water temperature control. If they can recover freezing cold water in the middle of summer, the water going to their customers is cooler. They have less microbial problems in their elevated and ground storage tanks because the water is cooler. A lot of places now using this for nutrient reduction. Ammonia, phosphorus, organic carbon. For some reason, those bugs underground, they love this stuff. It's like French onion soup. So anyway, we see attenuation of nutrients during ASR storage. And then just the big one is deferring expansion of water facilities. If you can delay by 10, 20 years the need to spend huge sums of money expanding a treatment plant just to meet a higher peak and just recover and meet that peak from ASR storage, you can save tremendous amounts of money. And then what we're seeing increasingly in recent years is the most reliable supply of water during dry periods is wastewater. So a lot of utilities now are looking at that as a resource. We've heard some talks on that at this conference, and recover this water for storage, or store the water and then recover it to meet irrigation and other needs. All right, for those of you who were at ISMAR 8, there was a presentation that I gave on Hilton Head right after it was constructed. Well, now we're several years into that, so I'm going to take a couple of slides and just tell you what's happened at Hilton Head, South Carolina. This is an island off the southeastern part of the United States. And basically, they were initially supplied water with a whole bunch of fairly shallow wells in a karst limestone aquifer. And then the saltwater intrusion moved in, and so far they've lost about half of the wells on the island. And the other half are expected to be lost due to major pumping occurring on the mainland. So what they did was to basically shift their water supply to stored water stored in a deeper aquifer. And the deeper aquifer is brackish. So that was a concern initially. Can we store water in a brackish aquifer and get it back out? And the answer was clearly yes. So anyway, for those of you who remember this presentation, I'm not going to show you a lot of new slides and new material, but this is basically what this first well looks like. And then this is a bunch of happy people when they pumped the first stored water back out of the ground and realized it was the same water that they had put in many months before. So everyone was pretty happy there. So as we look back now to that time in 2011, and I did an analysis of all of that daily operating data since then and plotted up the actual storage volume versus time. And for those of you who can see the numbers, it ranges from about 0 to 2 million cubic meters of water, and covers from 2011 to 2018. And you can see this sawtooth. They fill it up during the winter, and they drain it during the summer. And it's the same thing every year. You see that little red circle there right about 2013. We didn't suddenly lose 1 million cubic meters of water. What we had been doing in the prior time, was to build up a buffer zone, separating our stored drinking water from the surrounding brackish water. And we had about 1 million cubic meters of water in there that was like a donut around our stored water. And then it occurred to us, hey, you know, if the operators 5 years from now know they got 1 million cubic meters down there, at the end of the summer, if they need more water, they're just going to pump out the buffer zone. So we just went into the SCADA system and eliminated that 1 million cubic meters. It's still there, but when it gets down at the end of the summer and it gets to 0, he thinks he's out of water. And so it's just a little mental game we played. We didn't lose the water, we just preserved our buffer zone, and it works. So anyway, this is, I say it works, but basically it's looking at chlorides as the almost perfect tracer here. You can see that the numbers during recharge hover around 40 to 50 milligrams per liter. The chloride in the storage zone is at 685 milligrams per liter. And as the summer moves on and we recover more and more water, as we go out to 120 days during the peak summer months, the chloride creeps up. And during the last week, it goes up real fast because that front's coming back in. And so, but the highest numbers we've seen are about, somewhere between 170 and 200 milligrams per liter chloride. And their drinking water standard is 250. So anyway, they're very happy. I just met with them just recently, and they love their system. So of interest is, now, we all tend to have a picture in our mind of what happens. We've got this aquifer, we put the water in, it goes out, and then it comes back in. And what we know now from looking at the data and the monitoring and monitor wells and everything is that that's true, but we have some movement of water into the overlying confining layer and probably a little bit into the underlying confining layer. And that happens. And it's not a problem, but the water does move, not only laterally, but it moves up and down. And so we have a semi-confining layer, not a perfect confining layer. So anyway, in summary, after 7 years of operation, they've got consistent, excellent performance. They're storing drinking water in a brackish aquifer that's subject to saltwater intrusion, and they're getting 100% of the stored water back out each year. The storage periods range from 123 to 153 days, the recovery periods. And we're covering about 1 million cubic meters every year, and chloride concentrations from 184 to 230. So the interesting thing is we've seen a very slight trend of increasing specific injectivity. So what that means is that when we started out, the wellhead pressure during recharge was about, I'm going to use PSI because my mind doesn't work with kilopascals very well. But basically, just look at the numbers. There was 19.3 PSI at the wellhead to push about 7.6 megaliters per day into the ground. And now it's 10.5 PSI to do the same thing. So we've got a little dissolution of limestone in the aquifer around the well, which is just saves some money. As long as the wellhead doesn't collapse. So, all right, the success of that site then generated 2 more wells at the south end of the island. They thought that they were going to have another 30, 40 years, and all of a sudden they lost their first well to saltwater intrusion. They said, oops, time to move. So they put in 2 more wells at the south end, and this one happens to be in a floodplain. And so when the coastal surge from a hurricane came along, the ground elevation here is about 2 meters below this coastal surge level. So the well is up on a platform up in the air. That's a little unusual, but it's not that unusual. So currently in South Carolina, there are 8 ASR well fields and about 40 ASR wells in operation. South Carolina is just one of 25 states in the United States that have ASR well fields. There, as we can tell, there's over 500, probably around 700 ASR wells in the United States at about 140 different well fields. Okay, I'm going to talk a little bit about a current project. In fact, the construction of all the wells and wellhead facilities starts in earnest in 2 weeks. How am I doing? It's about out of time. Okay. So I left the little bell there. I know. Anyway, this project started a long time ago with the feasibility study, and we got around to last year completing a continuous wireline core and doing all kinds of geochemical and hydrogeologic testing, and put in a monitor well and geophysical logging, collecting all the baseline data for the site, designing the facilities last year, and now we're beginning construction of the full-size facilities. And there'll be cycle testing going on, and so probably in ISMAR 11 we'll have a presentation on that. But basically the challenge here is this is once again a seasonal storage, but the aquifer is high TDS, about 9,420 milligrams per liter. It's very tightly confined, and basically the aquifer is at depths of about 180 to 216 meters. Static water levels down about 10 meters. So we've done this before, but not in Texas. And people in Texas, they have a mindset that basically says, hey, if you haven't done it here, you got to prove it here. So that's where we're at. So anyway, this is a couple of photos from the continuous wireline coring, the results of the core log, pictures of the core, and so forth, just site pictures. The objectives, really, in addition to seasonal peaking, was drought storage. That's the big issue in Texas. It's long-term storage. Every few years they have a very severe drought that goes on for several years. So having done a detailed analysis, we determined that we needed to be able to recover water from storage for periods as long as 9 straight months. So we have very good upper confinement. There's no question about the water moving vertically upward, but the lower confinement is only 7 meters thick. And we've got cores through there. We've done geotechnical analysis on the cores. It's like a granite countertop. I mean, I can't imagine water getting through there, but that's in the core. What about the fault that might be out there 10 meters away? So that's kind of where we're at now. We've got to do the full-scale testing and find out how good is that confining layer. But all the data from other wells in this whole region of Texas shows this same confining layer being extremely tight. So that's where we're at. The other issue that we're looking at is the possibility of stacking the water, basically using this one zone that I described for storage and the zone underneath it, so that if we do have a failure in the confining layer, and after 7 months of pumping we start getting a higher TDS water, having water coming up from below, then what would be coming up from below would be fresh water, not salt water. So we'd have 2 zones stacked, one on top of the other. The other issue we'll be looking at is density stratification. Storing drinking water in a salty aquifer like that, we know that when that TDS differential is more than about 5,000 milligrams per liter, we're going to have the water tending to float like a pancake. And so what's the rate at which we lose water? It's probably a few gallons a minute, a few tens of liters per second, whatever. We've seen this before. We've dealt with it just by trickling flow into the water during a long storage period to make up for that. And there are other approaches to dealing with that, which Colin here has developed, and we're looking at those too. So another big issue we're looking at is what's the appropriate spacing between the wells. We want to push them close as we can together so that we have a big bubble that envelops all of the wells and moves out another 1,000 meters or so that we're pulling from the center of that bubble. But how close can we space those wells before we start having too much well interference and pull the water through that lower confining layer? So these are all going to be interesting things. A big challenge at this site is how do you dispose of water during well construction when it's 9,420 milligrams per liter TDS? There's no place to put it. So we found a wastewater treatment plant that was willing to take a lot of this water. So we'll be blending it. This is the wells here. We're talking about PVC casing, 610 millimeters OD. This is some large well casing pipe, about 180 meters deep. And anyway, that's it. So then the last one I'd talk about is in, okay, I'm going to turn it over here. I've got another 15 minutes. This is an interesting application. The issue here is not so much water storage for droughts, but the challenge is they want it to be subsidence neutral. And Galveston has already subsided about just over 2 meters. The Houston ship channel has dropped all around that area. Tremendous problems as a result of groundwater depletion over the last few decades. So they really want to do ASR to store water, whether it's for droughts or for floods. Either way, they just got wiped out 2 years ago with Hurricane Harvey. Houston was pretty much underwater. So water supply, fresh water supply was a problem. So anyway, the issue here, the challenge was, can we store water without causing further subsidence? And there was a big feasibility study just completed. We're dealing with very deep coastal plain sand and clay layers. So the approach here was to use it like an organ with playing different pedals in order to do what you achieve your goals. And so we'd have 5 separate ASR wells, all in different zones, storing the water. And each zone would have its own characteristics as far as TDS, as far as subsidence potential, and its applicability for short-term storage or for long-term storage. So these are the 5 formations. You can see the depths, you can see the TDS levels. So the shallow ones would have been the zones that had the most subsidence to date. They've had a lot of water level recovery due to regulations imposed to stop people pumping groundwater. And the concern here is that the subsidence may continue. Even though the groundwater levels have come back up, the modeling indicates that subsidence may continue for another decades or two, maybe 100 years or so. So how do you achieve subsidence neutral with ASR? Well, you'd have to do it in deeper zones that are already pre-consolidated because of their depth. And so it could be that the shallow aquifers are suitable for short-term storage, and the deeper aquifers are the ones you hit during a severe drought. So that's the concept. It's only a small part of the overall project that was done, and so I'm only talking about that part. This is a 6-hectare area, 10 wells. This is hypothetical. Nothing's been constructed yet, but 10 wells, 2 each in each of the zones, and you would operate that conceptually in order to achieve your seasonal or long-term goals. And then this is for a 19 megaliter per day well field, and if it worked, then you just plop these around the Houston, Galveston area to meet your regional needs, which might be 10 of these sites. So anyway, I already talked about some of the issues here, but as a result of the modeling, bear in mind there's virtually no geochemical data, no cores, so we're operating kind of blind, but just doing as best we can. And so that's obviously an early need to be implemented. But they did come up with a concept of an ASR credit because according to the modelers, and that wasn't a part of the project we were doing, that if you operate this in an ASR mode, there's going to be an increment less potential subsidence. And that could be converted to a credit, which could be set up as an inducement to a water user to implement ASR. So I think that's about it. Anyway, there's some other slides here which I'll just blow through, and then so anyone who's interested, these are some of the countries that are doing ASR. Some of the factors that have galvanized this is mostly economics, but it's also getting into a lot of other reasons why people are doing this. We're using a broad range of water sources for storage, and just about anything that holds water, we're storing water in terms of geologic applicability. And these are some of the operating ranges, storing water up to about 900 meter depth in some places. And you can see this. This isn't real, this is extra stuff. And for anyone who's interested, there's a great book out there that I just happen to have one more copy. And that's it. Any questions? Okay, I'm going to put on my other hat now. Any questions for that speaker? No question? There's one question I can see over there. Looks like I got about 10 minutes left.
Hi, David. With respect to long-term groundwater storage, what considerations do you look at with respect to hydraulic gradients and the potential for the bubble or the donut moving away from your recovery wells?
Yeah, big question, good question. With long-term storage, we tend to be looking into deeper aquifers, which usually, but not always, have much slower hydraulic lateral movement of the stored water. Most of the sites we're dealing with, we're looking at 1 meter per year, 2 meters per year. And if you have a bubble radius that's several hundred meters, it's not a significant factor. But we also have some other sites that are fairly deep that have a very high velocity. And that's obviously going to be pretty useless for long-term storage. So, you know, you need to do the hydrogeologic work to get values for porosity, get values for the local gradient, and do that analysis if not in your feasibility study, then at least flag that as a key issue to be addressed early in the project before you spend huge sums of money assuming the water will be there 10 years after you put it in there and find out the hard way that it's really several kilometers down the hill. So this is a big issue, but by going deeper, we tend to head off that issue. If you store water very shallow, then you tend to be dealing with much higher lateral velocities. And also, if you store water shallow, you're competing with that same aquifer with lots of other users. So by going deep, you tend to get into aquifers that may be poor quality, they may be salty, but no one's using them because of the poor quality. Okay, Peter, you're up. Okay, he's my good friend Peter Stuyvesant, and he's going to regale us on geochemistry.
Another question, please.
There's another question?
See, what is the range of pressures you utilize for injection?
Excuse me, would you say that again?
You talked about the pressure injection under different confined aquifers. So what is the range of pressure you are applying actually for injecting water?
Okay.
And how it varies with reference to the confined head of the, piezometric head of the confined aquifer. Just some basic, information about that.
We tend to try to limit the pressure on the wellhead. We seal the wellhead, but we try to limit the pressure on that to about, say, 2 bars, 20 psi, whatever. Just for mechanical reasons. You can take it higher than that. You just have to design the wellhead to hold the higher pressures. The highest we've ever gone was like 3 bars, something like that.